we can now write down our portfolio equations for two assets or for more than two assets. So now I know that when I have three assets, the expected return of the portfolio, it's still the weighted average. It's the weight of 1 times the return of 1, the weight of 2 times the return of 2, and the weight of 3 times the return of 3. But my risk equation now has the 3 variance terms and the 3 cross terms, 1 with 2, 1 with 3, 2 with 3. And remember that I've doubled all of these to account for the fact that I have 2 of these, but only 3 unique. When I have 4 assets, I add 1 more term to my portfolio return equation. I add 1 more variance to the first line of my portfolio risk equation, but now instead of having 3 unique cross terms, I now have 6 unique cross terms. So I have 1 with 2, 1 with 3, and 1 with 4, 2 with 3, 2 with 4, and then 3 with 4. And remember, these are all doubled because 1 with 2 is the same as 2 with 1. And so I have n expected returns, n standard deviations and variances, and n squared minus n over 2 correlations or covariance terms. Here's another way to look at the number of cross terms. Remember that the number of cross terms is going to be n squared minus n over 2. Well, if I have 2 assets, then it's 2 squared minus 2 over 2, and that's just going to be 4 minus 2 is 2 over 1 is going to be 2. And so if I have 2 assets, I can see I just have 1 connector between them. If I have 3 assets, that's going to be 3 squared, which is 9, minus 3 is 6, over 2 is 3, and I can see that there are 3 connections between them. If I have 4 assets, 4 squared is 16, minus 4 is 12, over 2 is 6, and I can see that I have 1, 2, 3, 4, 5, 6 relationships between them. And if I have 5 assets, then that's going to be 5 squared is 25, minus 5 is 20, over 2 is 10, and I can see that I have 1, 2, 3, 4, 5, and then 6, and then 7, and then 8, 9, and then 10 relationships between them. We're going to skip a bunch of the proofs and a bunch of the math, and I'm just going to talk about what happens next. When we add more assets, we can't make a worse opportunity set. We can only make our options better. If adding a third asset, a fourth asset, a fifth asset doesn't make our allocations better, if it doesn't move this efficient frontier further to the left, then don't add it. And if people don't add the stock, the price goes down. A lower price stock will have a greater future return, and so the stock becomes more attractive, and then it gets added. And so the point is that if I have all these individual assets and I have some relationship between them, adding more and more assets pushes this minimum variance or efficient frontier further and further to the left. So here's the idea. In risk return space, if I start with 2 assets, there's a relationship between them. And this is the opportunity set that's available between these 2 assets as a function of each asset's expected return and risk, and the correlation between the 2 assets. I can add a third asset, and if I add a third asset, I get a relationship between each of these. And then I have some sort of global relationship between them. And if I add a fourth asset, I get all the individual relationships, but then there's also some sort of global relationship. And as I continue to add more assets, then my relationship can't get any worse. I can't do any worse than I would have done with the previous assets, but adding another asset, wherever it might be, is going to push my frontier at least a little bit to the left. And as I add more and more and more assets, I continue to push my frontier slightly to the left, until I've added all of my assets and I end up with my global efficient frontier as a function of every single asset and all of the relationships between them. And from this, I can find my global minimum variance portfolio, which is the portfolio that's most to the left. And now that I have n assets, and so n expected returns and n standard deviations and n squared minus n over 2 correlations or covariances, I can now try to figure out, given a single risk-free asset, where I want to be on this line such that I produce the steepest sloped cal. And remember that this is going to be my P star portfolio, and the cal slope is going to be the expected return of P minus the risk-free divided by sigma P. And I have a big nasty equation that's going to give me the expected return of P, and I have an even nastier equation that's going to give me the variance or standard deviation of P. But from all of these, I can figure out the optimal weight of the first asset, weight of the second asset, and all the way through to the weight of the nth asset. That's going to give me my maximum slope. And so that's what we'll talk about next. So as we add more assets, we push our efficient frontier further and further to the left. And given some n assets, we have an expected return. We have n expected returns. We have n standard deviations. We have n squared minus n over 2 correlations. And from this, we can figure out P using the above equations. Note that the slope function does not change, but the expected return of P gets bigger relative to the number of assets. Every time we add an asset, we add another weight and another return. But for the portfolio standard deviation equation, every time we add another asset, we're going to have, well, n of the variance equations, variance terms, and we're going to have n squared minus n over 2 of the covariance or correlation terms. And so that equation is going to get big and nasty. Now, to figure out how to come up with a maximum slope, we'll need to substitute the expected return of the portfolio equation into here. We'll need to substitute the standard deviation of the portfolio equation into here. And we're going to have to solve for the W1, W2, W3, W4 star that gives us our optimal maximum slope. The trouble is that we can't just substitute the way we did before. We substituted for W2 and we had our objective function, which was our slope function, in terms of a single choice variable, W1, and it was relatively easy to do the calculus. But now we would have to do this in a much more complicated way. For example, if we have 3 assets, I can't substitute all for W1. I would need to differentiate, but I would also have to have essentially a budget constraint that means W1 plus W2 plus W3 all sum to 1. And so it's too many W's to do easily on paper, so we're going to use a computer. We're going to use Excel. And so we're going to rewrite the portfolio standard deviation function in a form that's much easier in Excel. And so instead of essentially typing in this awful equation for 4 assets, or this equation for 3 assets, what we're going to do is we're going to write these equations in matrix form, and then we're just going to highlight and sum them and then take the square root of the sum. And that's going to make it much easier to compute the portfolio standard deviation in Excel. So for example, if we have a 3 risky asset example, here's our portfolio risk equation from before, but we can write this as sigma 1,1, sigma 1,2, sigma 1,3, and then I can just multiply the weights. I can have W1, W1, sigma 1,1, W1, W2, and this equation here is exactly equal to this equation here, but written in this slightly different form. Here I have 1, 2, 3, 4, 5, 6 different terms that I'm adding together. Here I end up with 9 terms because I'm not combining the cross terms, but we're going to see that this is a much easier way to do this in Excel. And all I have to do is highlight these 9 cells, take the sum, and then take the square root.